Hi everyone! Today our group will present about nuclear physics in chapter 24. In this chapter we have 3 subtopics which are nuclear, structure, radioactivity and also nuclear reaction. And my name is Anur Izzati binti Umar and I will present about nuclear structure, and for the other 2 subtopics which are radioactivity will be explained by Isha Erika, and for the last subtopic which is nuclear reactions will be explained by Camelia. Okay, now we look at nuclear binding energy. Energy binding is EB, that energy required to split a nucleus into its individual proton and neutron. Energy released when nucleus is formed from its individual protons and neutrons. In the simplest word, that EB is energy required to split the nucleus apart. And when we supply some energy, we also supply some mass. So in energy, it has mass. So what is mass defect? Mass defect is a delta M, where is the difference between the sum of the masses of individual nucleons, which are proton and neutron, that form an atomic nucleus, and the mass of the nucleus. So delta M represent the mass of the binding energy nucleus. Recall that the energy and mass are related by the equation E equals to mc squared, where c is the speed of light.
Now, let's look at this example. Calculate the total binding energy for the nucleus of radon. First thing first, we need to find the neutron by subtract the mass number with the atomic number. Then, we need to find the delta M. So, we need to find the ZMP and the NMP, which are the proton number times with the mass of proton and the number of neutron times with the mass of neutron. After that, we can find the total of ZMP and NMP. After get this answer, we can calculate the delta M by the equation of ZMP plus NMP minus with the M of nucleus. And finally, we can calculate the energy binding by the equation of delta M, binding energy by the equation of delta M c squared, and we can get the answer. That's all.
And before I end my part, I want to touch a bit about radioactive isotope. Radioactive isotope is unstable isotope, emit radioactive radiation, and radioactivity was the result of the decay of unstable nuclei. For example, the radioactive isotope is a cobalt-60, iodine-131, and also a carbon-40. That's all from me. Thank you. And I will pass to Isha Erika to continue our presentation.
Hi everyone. Do you guys know about the 3 types of radiations? First type is alpha particle, second type is beta particle, and the third type is gamma ray. So, alpha particle is a positively charged of helium nuclei. Beta particle is a negatively charged of electron, and gamma rays is a very high energy of photon. So, next is about half-life. Do you know about half-life? So, let's check it out. So, basically, half-life is time required for half of a sample to decay. So, the half-life is actually depends on the sample we use. So, this is the one of the example when the thorium is turning into protactinium by beta decay. So this is, let's say we start with 80 gram of thorium. So after 24 days, it's gonna left by half into 40 gram of thorium. So another 24 days, it's left 20 gram of thorium. So another 24 days, it's left by 10 gram of thorium. So we can say that the half-life of this decay is 24 days. So for someone that have visual type of person, so we can see this is the graph of half-life for thorium turning into protactinium. So we can see this is the amount of the thorium at restart. So by one half-life, so it's decreased by half. So another half-life is decreased by half, and another half-life it decreased by half. Okay, we're gonna look at the formula of the half-life. So A is determine activity of a half-life. Or we can say this is the rate of the decrease in the number of nuclei is proportional to the number of nuclei present. So the N is the number of nuclei, and it is the time change. Or we can conclude that this is negative lambda n, which is n is the number of nuclei, and the lambda is a decay constant. So A is refer to the activity, and n is refer to the number. So A is expressed of its activity, and N is the initial activity of the nuclei. So this is the exponential and to the power of negative lambda t. Or we also can express this by number of nuclei. This n is the number of nuclei, and N is the initial number of nuclei, exponential to the power of negative decay constant times of t. So another equation is equation of half-life itself. So after derivations, we can get the half-life is equal to ln 2 over decay constant, or we can simplify as ln 2 is equal to 0.693 divided by lambda. So next we're gonna look at the uses of the radioactive decay. First uses is carbon dating. We use carbon dating to determine the actual or absolute age of the object. Or maybe you can say that if you found a fossil, then we want to know the actual age of the fossil, so we can use carbon dating. So the second one is radioactive tracer. We use beta particle and gamma ray to trace the chemical reaction in our body. So maybe in medication, we put radioactive tracer in our body so it can trace whether it has a chemical or not. So the last one is smoke detector. So when the smoke enters the chamber, which is content of alpha particles, so the current will decrease, then the alarm will sound. So we know that there is a smoke.
Hi guys, now let's move on to nuclear reactions. Did you know that it's possible to change the structure of nuclei? These changes are called nuclear reaction. Nuclear reaction occur when a bombarding particle strikes another nucleus. This equation says that an alpha particle strikes a nitrogen nucleus and produces an oxygen and a proton, which is hydrogen. This nuclear reaction starts with two stable isotopes, helium and nitrogen, and produces two different stable isotopes, hydrogen and oxygen. Nuclear reactions in which energy is released are said to be exothermic reactions and are characterized by positive Q values. Reactions with negative Q values called endothermic reactions. Have you heard of nuclear fission and nuclear fusion before? Well, nuclear fission means the splitting of atomic nuclei. This is the process by which energy is generated in nuclear power plants. Meanwhile, nuclear fusion is exactly the other way around. Nuclear fusion is when two low-mass nucleus combine or fuse to form a more massive nucleus. Fusion reaction requires extremely high temperature. So here's a fact. One of the examples of fusion reactions occur in the sun. Maybe you guys have been wondering what exactly happened in these two processes.
Alright, let's recap a bit about the structure of an atom. In the center, there is an atomic nucleus. These atomic nucleus are going to split or to fuse together with another nucleus. Nuclei consist of nucleon and protons. The protons are positively charged, while the neutrons have no charge, which means neutrons are neutral. Thus, the atomic nuclei is positively charged as a whole. There are electrons around the positively charged atomic nucleus. They are negatively charged. Now, let's get back to our point, nuclear fission and nuclear fusion. Let's first look at nuclear fission. There are single neutrons hit the atomic nuclei. This is resulting in the splitting of atomic nucleus, and then two nuclei will produce. Each nuclei takes part of the electrons with them. So, two new atoms are formed. Let's look at the case of some very large atoms. A few neutrons are additionally released. When uranium atoms are split in nuclear power plant, it involves the release of 3 neutrons. This will lead to the next fission process in a chain reaction. Finally, energy is released. Here's some fun fact. 1 kilogram of naturally occurring uranium has the energy of 12,000 liters of mineral oil, or almost 19,000 kilograms of hard coal. Now, let's us discover about nuclear fusion. Like I said before, nuclear fusion is exactly the other way around. It only works with small atoms, for example, hydrogen. The atomic nucleus only consists of 1 proton. If we want to force these 2 protons together, these 2 would repel each other. It is because they have an equal charge, and remember, equal charge repels. Referring to this case of magnet in atomic nuclei, we are now talking about Coulomb force. Based on this force, it is like these protons have fans around them. So, in nuclear fusion, it needs something that would force these protons so closely together and to break down the fans. When this happens, the protons come closely together. There will be strong interaction. This makes sure these 2 nucleus can combine together and form a new atomic nucleus. That's all from us. I hope you guys enjoy and understand what we are trying to deliver to you. Thank you for watching. Bye bye.